time for us to do some practice. Woo! Yeah, the more we practice, the better we get. So I hope you're ready. Make sure you have your table of Laplace transforms handy, because this will be like what you see on the test, and these are the formulas you'll be given. And, well, let's get going. First problem. Solve the differential equation x double prime plus 2x prime minus 3x is 12e to the t. And the initial conditions, x of 0 equals 12, x prime of 0 is negative 5. All right. So one of the things we should hopefully learn is how to identify the type of problem that we're doing. And here, there's a big clue. This part right here says, oh, this is a non-homogeneous problem, because we have, this other function on the side. And so what's the idea? Well, for the non-homogeneous, there's really two techniques available. There's the variation of parameters, which is, and the method of undetermined coefficients. Now, I don't want to make variation of parameters sound like a scary thing. It's a little bit tricky and a little bit more labor-intensive. Method of undetermined coefficients says, hey, if our function is nice, and then what we can do is we can guess the solution, and life is good. And it turns out e to the t qualifies as nice. So where do we go? Well, what we'll do is we'll start by doing the homogeneous problem. So we'll look at x double prime plus 2x prime minus 3x equals 0. Turn this into a polynomial, r squared plus 2r minus 3 equals 0. And what would you know? It actually can factor. Almost as if they wanted it to factor. Yes, you should anticipate that the problems are going to be nice. So this factors as r plus 3 and r minus 1 equals 0. And you can check r squared, good. Then you have minus r plus 3r, which is 2r, and minus 3. All right, so what are the roots? The roots are negative 3 and positive 1. But really what that tells us is that we have solutions. So the solutions are e to the minus 3t from the root of minus 3 and e to the positive t. All right, so now we know what the homogeneous solutions look like. So in particular, we can say that yc looks like some constant e to the minus 3t plus some constant e to the t. All right, homogeneous part is done. Now we transition and say, all right, let's tackle the non-homogeneous part. And so for that, we say we need to guess a solution. And I don't know why I put y here. That should be an x. X, C. There we go. So, particular solution. All right, x, p. Now, how does this work? Well, what you do is you look at the function and you say, all right, write that function down. And then there's sort of three things you have to do. If there's a power of t involved, make sure you have all lower powers. If there's a sine or a cosine, make sure you have the other one. So if there's a sine, add the cosine. If there's a cosine, add the sine. And then the last thing is check for bumping. So right now, it's just e to the t. There's no powers of t. There's no sine cosine. And so our particular solution looks like something e to the t. Okay, I'll put some constant c. But we have to check to see, is there overlap? We say, there is overlap. And here, bumping is very straightforward. Bumping just means multiply by enough powers of t until there's no more overlap. So we're going to multiply by a single t. So that says our particular solution has the form, some constant t e to the t. And now we just have to figure out, all right, what's the right choice for c? So for that, we're going to plug it into our differential equation, which means we need to do x prime and x double prime. So xp prime, product rule, derivative of the first times the second, plus the first times the derivative of the second. Derivative of e to the t is e to the t. Second derivative. All right, well, derivative of e to the t is e to the t. And now product rule again. Derivative of the first times the second, plus the first times the derivative of the second. which we can write that as 2c e to the t plus c t e to the t. Now plug in. So we're going to get our 2c e to the t plus c times t e to the t. This is our x double prime plus, there's a 2 times x prime, c e to the t plus c times t e to the t. And then there's a minus 3 c t e to the t, and that needs to equal 12e to the t. Okay, at this point, we start to gather. And we say, well, what happens? Well, if we look at our c times t e to the t, we have one of them here, then we have two of them here, and minus 3 of them there, which means those all cancel. And they should. You know, there's no t e to the t over there. And so they should somehow disappear, and that's what will happen. And that's why the bumping works. Now, what's left? Well, we have 2c e to the t and 2c e to the t, which makes 4c e to the t. And we want that to equal 12 e to the t. And now we sort of say, what value of c makes this work? Well, no surprise. We see, aha, c equals 3. So now, plug that back in, and we come to our conclusion that this should be 3t e to the t. All right, so we have our complementary solution, our particular solution, and their powers combined. We get our solution. So we're doing great. So we can say x has the form some constant e to the minus 3t, some constant e to the t, and then plus 3 times t e to the t. Now, the last thing we need to do is deal with the initial conditions. We haven't talked about the initial conditions yet, and they come and play right at the very end. All right, well, so we'll need to look at x prime, so we'll do that too. X prime minus 3a e to the minus 3t, b e to the t, and here we'll have 3 e to the t, the root of the first, times the second, plus the first times the root of the second. All right, well, plug in 0. Well, we're going to get a, b, 0, because e to the 0 is always 1, and then that t makes that term 0. So x of 0 is a plus b, but that needs to equal 12. X prime is 0. Well, minus 3a plus b plus 3 plus 0. So that's minus 3a plus b plus 3, but that needs to equal negative 5. All right. Well, great. This isn't so bad. And, okay, we can rewrite this if we wanted to. We could say, all right, that's the same as a plus b equals 12, and minus 3a plus b, move that across, subtract 3 from both sides, is minus 8. Well, we can combine. In this case, there's a really simple way to combine. If we subtract, a minus minus 3a makes 4a, b minus b makes 0, 12 minus minus 8 makes 20. So we say, aha, a should be 5. Once you know a equals 5, plug it in. 5 plus b is going to equal 12. So that says b has to equal 7. And so now we know our a and we know our b, and therefore we know everything. And so the last thing to do is to write down our final answer. So we can say x has the form of 5e to the minus 3t plus 7 e to the t plus 3t e to the t. And that's it. We're done. Wow. Great. Nice problem. Nice problem. And, generally speaking, we do try to write problems in such a way that they work out fairly nicely in the end so that we'll get a reasonable answer. Our goal is not to give you crazy numbers. Our goal is to say, hey, can you do the math? And do you understand the processes? All right. So, okay, recapping what we did. If we see there's a function, non-homogeneous, figure out whether we want to do variation of parameters or whether we want to do method of undetermined coefficients. Generally speaking, if this is a simple function, method of undetermined coefficients, run the homogeneous. You need this just to check for bumping. Figure out the form, plug it in, figure out the constants. Then if you do have initial conditions, run through and find your initial conditions. And then you're done. All right, one problem down. 5 to go, right? Yep. Because that's like the test. The test will have 6 problems. So, we should make it, if it's going to be a practice, we should practice like what the test has. Okay, number 2. Consider the following system of equations. X double prime plus y double prime minus x prime plus y equals natural log of t squared plus 1. X prime plus 2y prime plus 2x equals e to the minus t. Honestly, kind of hopeless. That natural log t squared plus 1. Not feeling the vibe with that one. Well, what are we supposed to do, though? Using the method of elimination, find a single differential equation for y, not involving x in any way. And you do not have to solve this differential equation. I really like reading the directions, especially whenever they have the word not. That's like hey, we know this is hard to do. We don't expect you to do it. So, woohoo, nice. All right, so what's going on here? Well, we're going from 2 equations with 2 variables. We want to get down to 1 equation, 1 variable. Okay, so that's the idea of elimination. In essence here, we want to get rid of the x. And it's not like a clean way to do it automatically, at least it doesn't look like there's a clean way to do it by some, add, subtract, or substitution. But that's okay. So what we can do is we go and say, well, what's going on here? Well, we start by rewriting it. So we're going to group x's and y's. So x double prime minus x prime plus y double prime plus y equals natural log t squared plus 1. And below, x prime plus 2x plus 2y prime is e to the minus t. So put the x's together, put the y's together. All right, no big surprises. Okay, and now we're going to switch to using our d notation. Remember, d, capital D, is a placeholder for saying, hey, we're taking a derivative here. So x double prime would be d squared x. X prime would be dx. And in particular, we can write this as d squared minus d times x. Here, y double prime plus y, d squared plus 1 times y. Downstairs, we'll have d plus 2x. And here we'll have 2 times dy equals as before. So now you might say, okay, well, why do that? Well, what we have is we have 2 equations with 2 unknowns. We think of x and y as our unknowns. And so we've turned our derivatives into coefficients by using this d notation. And that's what's happening with this method of elimination, is to say, oh, somehow turn derivatives into coefficients so that you can use your techniques that you've learned before. And for our technique, we're essentially doing some variation of Cramer's rule. So we're after a differential equation for y. So what we'll do is we're going to take a little 2 by 2 determinant, where we're just going to write down these coefficients, d squared minus d, d squared plus 1, d plus 2, and 2 times d. And that's times by y is going to be equal to, now on the other side, we're going to do something similar, except if we think about it, this first column is associated with the x. The second column with the y. So we're going to replace the y part by the functions. So d squared minus d plus 2. That column is with the x. That stays as is. Natural log of t squared plus 1 e to the minus t. All right. So if we can figure out what's happening with these two sides, we're actually in pretty good shape. We're going to be done. So that leaves two determinants for us to work with. Let's start with the one on the left. Okay, so we'll do this. D squared minus d plus 2, d squared plus 1, 2 times d. And it's determinant as always, right? You know, got your diagonals. So add, subtract. So we're going to have d squared minus d times 2 times d, subtract d squared plus 1 times d plus 2. And we're going to do some multiplication. So we'll get 2d cubed minus 2d squared. Then here, minus d cubed. And then you're going to get 2d squared, so subtract 2d squared. And then plus d, but there's a subtract. And a minus 2. And now we look, 2d cubed minus d cubed would be d cubed, minus 2d squared minus 2d squared, minus 4d squared, and then minus d, and minus 2. All right, so there we go. Those are our coefficients. Now what? Well, the other thing is the other side. Okay, so we'll work on that. So we're going to have d squared minus d plus 2, log of t squared plus 1, and e to the minus t. So we should do this as d squared minus d times e to the minus t, subtract d plus 2 log t squared plus 1. So again, remember d stands for derivative. So this says take two derivatives of e to the minus t. Well, every time you take a derivative, a minus comes down. So if I take two derivatives, this would be e to the minus t. Now subtract if you took one derivative. Well, a minus would come down. So subtract a minus makes a plus e to the minus t. Then subtract, so a derivative of natural log t squared. So natural log, easier to take derivatives. Function goes downstairs. Derivative of the function goes upstairs. Then subtract 2 times the function. So that would be what we have. Okay, so that's the right-hand side. And now we put everything together and we're good to go. We can actually write down our answer. So remember, this part is multiplied by y. So if you imagine, you say, oh, if I imagine writing a y here, what would we have? Well, we'd have third derivative of y, so y triple prime, minus 4, d squared means second derivative, minus first derivative, minus 2 times the function. Okay, that's the left-hand side, equals the right-hand side. Well, there's 2 e to the minus t, then minus 2t over t squared plus 1, and minus 2 natural log t squared plus 1. And there we go. That says, look, the function for y that we're looking for has to satisfy that differential equation. And good news, we don't actually have to figure it out, because we'd have a challenge trying to do that. So, woohoo! We did it! We did it! Nice! All right, well, that's 2 down. 2 down. So, what's the moral here? If you do see something where it's method of elimination, set up. You know, write everything in terms of this denotation, so you really have this nice system. And then we say, okay, we really do a variation of Cramer's rule and carry out the computation. In some sense, the derivative where we just have the d's, nothing too surprising happens there. It's like what you think it should be. When you have functions, just be careful. So it's going to be the parts involving d, and then you put the function after it. So you know that we're really taking the derivatives of the function. So you don't want to have the e minus t on that side. You want to make sure you have the e minus t on that side. That's the only thing to be careful about. All right, great. Woohoo! All right. Well, we can't celebrate too long, right? We've got 4 more problems. You got problems. We got to keep going. So, number 3. Find the eigenvalues and the corresponding eigenvectors for the matrix A equals 1, 6, 9, 4. And then there's part B, which says circle the direction field from the choices below corresponding with x prime equals ax. So part A, there's no differential equations involved. This is all about our linear algebra skills. Okay, so let's work through it. So we'll start by eigenvalues. So we'll look at, you can look at lambda I minus a or a minus lambda I, whichever one you prefer. They're both going to be giving you what you need. And so let's do lambda I minus a. That's what I do. There are people who are going to be very insistent that that's the correct one. And no, you can do either one. Okay, so we're going to take the determinant of that, and we're going to set that equal to 0, and that will give us our eigenvalues. Okay, so this is the determinant of lambda minus 1, minus 6, minus 9, and lambda minus 4. Okay, so 2 by 2. No big surprises. Lambda minus 1, lambda minus 4, and then subtract minus 9 times minus 6. All right, well, multiplying out here, we'll get lambda squared minus 4 lambda minus lambda makes minus 5 lambda, and then we'll have a plus 4. And then we're going to have a big number here. 9 times 6 is 54. Okay, and then we're going to subtract 54. Oh, all right. So we'll get lambda squared minus 5 lambda minus 50. Okay, but that's not so bad. Now, does it factor? And, 50 is a bigger number than we usually encounter. But if you remember how it works, we need 2 numbers that multiply together to give us minus 50, but add together to give minus 5. Minus 10 and 5 do it. So that would say it's lambda minus 10, lambda plus 5, right? They multiply together, give minus 50, and minus 10 lambda plus 5 lambda gives minus 5 lambda and lambda squared. So yeah, good. It works. Yay! Okay, so what do we have? Well, we should make some notes here. We'll have our eigenvalues, I'll abbreviate that as E values, are going to be 10 and negative 5. Then we're going to have our eigenvectors. Okay, so with the eigenvalues done, now we swap over and start doing eigenvectors. And for this, we have to do it for each case. And all right, let's suppose we start with 10. So I want to look at lambda I minus a. And so in particular, that would be what? Well, it would be 9, because 10 minus 1, and minus 6, and minus 9, and plus 6. This is lambda I minus a. And then I'm going to do a little bit of work here, 0, 0. And so this is the augmented matrix approach. There's other approaches here. But we see, okay, that row knocks out. And so what we're really saying is if we have an eigenvector of the form AB, then what we would have is that 9a minus 6b equals 0. Can we think of numbers where 9 times a minus 6 times b equals 0? Well, I can think of some numbers that do it. So one way to do it is say, okay, use the coefficients to sort of cross over. So if we can do that, we can say, all right, if you let a equals 6 and b equals 9, that works, 54 minus 54. So we can say, all right, do 6, 9. Now, how do you check, right? If you're nervous, you're in a test, your heart's racing, you're like, boom, 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 boom. How do you check if you have the right eigenvector? Well, think about coming up here and multiplying it by 6, 9, and what do you get? You get 6 plus 54. That would be 60. And here you get 54 plus 36, which is 90. And then you say, oh, I did multiply by 10. We got it right. Woohoo! Yeah! It's nice to know you got the right answer. All right. Now, of course, the eigenvector isn't unique. You can take any multiple of 6, 9. So, for instance, we could have also chosen, since both of these have a factor of 3, we could have also chosen 2, 3. That works just as well. All right. So there's the eigenvector for 10. How about for negative 5? Well, we're going to do something similar. And for lambda equals negative 5, well, what will we have? We'll have minus 5 minus 1 is minus 6. And we'll have minus 6, minus 9. Minus 5 minus 4 is minus 9. And I like to do augmented matrix here. And again, aha, we can knock out a row. They're multiples of each other. In fact, we can divide through by negative 6. And see, we get 1, 1, 0, 0, 0, 0, which really says what? It says a plus b has to equal 0. So I can choose a choice for a and b, like what we did here. Or what we could have done is we could have said, hey, that really says a equals minus b. So if I look at a solution ab, that can be rewritten as minus bb, or as b times minus 1, 1. So that would be the eigenvector. And it's easy to check. It works there. All right. Good. So there's the answer to part A. There's still part B. Okay, so how are we going to do part B? Because we don't have a lot of space. Well, let's look at the pictures. So we have to look at the pictures. One way we can at least simplify is to say, can we knock anything out? Well, notice on this picture, everything's going out. What does that mean? If everything's going out, that means that all the eigenvalues would have to be positive, because everything goes away. And we know we have one positive and one negative. So it can't be this one, because that doesn't have a negative eigenvalue. If you have a negative eigenvalue, something should go in. If you have a positive eigenvalue, something should go out. And if everything goes out, you have all positive eigenvalues. If everything goes in, all negative eigenvalues, well, that's the picture of everything going in. So that one can be knocked out as well. So it's not those two. So now we're down to these two. And they're close to each other. And so we just have to sort of say, okay, but which one is right? So this is where we come back and look at our eigenvectors and eigenvalues. And what we can do is we just do a quick sketch. So I'll do a quick sketch here. And we say, all right, let's look at our direction. So negative 1, 1. That says over negative 1 in the first direction, up 1 in the second direction. So that's this line here. So there's the negative 1, 1 line. The eigenvalue is negative 5, which means that in this direction, this corresponds to the direction x1, negative 1, x2, positive 1. Right? In that direction, negative eigenvalue means you head to 0. So the arrows should point in. Now, for completeness, we actually have enough to answer the question now, but for completeness, this direction says over 2, up 3, And so we're going this way. All right, so that's the direction 2, 3, right? 2 in the first direction, 3 in the second direction. Eigenvalue is positive, so that says if we're there, we need to point out. We're going away. So in that case, we're going to have our arrows pointing that way. So there we go. We know these two directions. We know how they behave. And actually, once you know the eigenvalues, eigenvectors, that gives you the behavior in two directions, but now you can figure out other directions as well. So we don't need this, but for example, we're going to do things like that. So that's our behavior. That's how things should behave. So you say, okay, that should be a rough sketch. And now we look here and say, which one matches? Well, all right, along this line, we should be going in. That one's going out. So that's not right. You can also see in this direction, we should have a direction roughly here where we're pointing out. Well, that's not happening either. So it's not this one. By process of elimination, it has to be that one, but let's see if it matches the picture. Just, for completeness. We go in along that line. Good, that's matching. And then along this line, we're going out. Yep, that's matching the behavior. And we see that the curves are doing what we expected to do. So this is the right answer. There we go. Done. Done. All right. Woohoo! Got a little bit too excited. I overlapped my 10 a little bit. Oh, that's okay. We can still see that it says 10. All right. Nice. A picture problem. It's nice to have a picture problem sometimes, right? We love picture problems. Okay, we're halfway done. Woohoo! How you doing? Are you hanging in there? I hope so, because we still have half to go. And it's probably the fun half. All right. Number 4. For any matrix A and value lambda, it is always the case that if you look at e to the at, so that's a matrix, it's e to the lambda t, now that's a function, times e to the a minus lambda it. And so that's sort of like oh, cute. Now, you don't have to prove this. This is just, it's a statement that's been given to us. And now, what do? Well, using this, or by other means, determine e to the power at, where a is the matrix below, which has eigenvalues 4, 4, 4. Now, you might say, aha, I'm going to use other means. Okay, you can. You totally can. But let's actually do this and see what happens. So what does this say? Well, we know the eigenvalues of the matrix because it tells us to us. It's 4, 4, 4. You say, all right, well, since it's 4, 4, 4, then according to this, we have, if we call this A, then what we would have is A minus 4I, because it's true for any lambda. We should be using that lambda. See, lambda is often associated with the eigenvalue. So all right, let's do that. What would that be? Well, what you'll have, 12 minus 4, 8, and minus 3, minus 5, 6, minus 2, minus 4, 10, minus 4, minus 6. All right, so there's our a minus 4i. Now, what's nice about this? Well, if you think about what's going to happen to the eigenvalues, what you should expect is that the eigenvalues should all go down by 4, because you subtracted 4 times I. So far, all our eigenvalues before were 4. All the eigenvalues here are 0. And what's one of the things that we're learning in this class? 0 is a friend. We like things which are 0. And so how is that a friend with matrices? Because you might look at them and say, there aren't any zeros here, Steve. How are all the eigenvalues 0? Well, what we're going to see, and it's coming, is if all the eigenvalues are 0, excuse me, if all the eigenvalues are 0, what will happen is that in a relatively short time, if you raise this power, matrix to a power, it just goes away. Okay, so here's our game plan. We have e to the at. We're going to use this with lambda equals 4. That's e to the 4t times e to the a minus 4i times t. So that's just the definition. And now the question is, well, how do we compute this? Well, if all the eigenvalues are 0, the answer is you don't have to do anything fancy. You just have to compute some powers. Because, as I recall, we'll make a note here, if I have e to a matrix, b times t, that's the identity matrix, plus, and then it's going to be b times t, plus b t squared over 2, sorry, there's a b squared here, and so forth and so on. This would be t cubed over 6, which is 3 factorial, dot, dot, dot. So what we want to do is say, hey, does something happen to these matrices? And the claim is if all the eigenvalues are 0, something does happen. And it's a good claim. It's true. Well, for us, it means we're going to be doing some matrix multiplication. Okay, so let's start with a minus 4i quantity squared. So 8 minus 3 minus 5, 6 minus 2 minus 4, 10 minus 4 minus 6, and 8 minus 3 minus 5, 6 minus 2 minus 4, and 10 minus 4 minus 6. All right. Well, now it's a matter of just being patient. 64 minus 18 minus 50. All right, again, I'll say that one more time. 64 minus 18 minus 50. So that's 64, subtract 58. 6. Minus 24 plus 6 plus 20. So that's minus 24, and then we're going to add 26. 2, right? Minus 24 plus 6 plus 20. Yeah, that's 2. All right. Good. Let's see, do I just have to double check? This is the danger when you do everything in your head, right? Okay. Then we have minus 40 plus 12 plus 30. So minus 40 plus 12 plus 30 is 2. Uh-oh. Made a mistake here. Let me fix that. This is what happens when you try to do numbers in your head, right? So let's be a little bit more careful with this entry here. 64 minus 18 and then minus 50. So really that's minus 68. 64 subtract 68. It's not 6, it's negative 4. Okay, all right. I feel better about that first row. Well, let's put in the second row. Okay, 48 subtract 12 subtract 40. Okay, so first off, 48 subtract 40 is 8. Subtract 12 makes negative 4. Minus 18 plus 4 plus 16. Well, plus 4 plus 16 makes 20. Subtract 18 makes 2. 30 plus 8. Minus 30, because there's a minus sign here. Minus 30 plus 8 and plus 24. So that's 32 minus 30 makes 2. And last we have 80 minus 24 minus 60. Well, 80 minus 60, that's not so bad. 80 minus 60 is 20. Subtract 24 is negative 4. Minus 30 plus 8 plus 24. So that's minus 30 plus 32, which is 2. and minus 50 plus 16 plus 24. So minus 15 minus 50 plus 16, oh, not 24, 36. 16 and 36 makes 52. Subtract 50 makes 2. Oh my gosh. Oh. Be careful with your arithmetic. Be careful. It's easy to make mistakes. All right. A minus 4i cubed. Now you're probably starting to like, ah! Wait, are we going to have to do this on a test? And the answer is, well, we try to put harder problems in the practice so that when you get to the test, you're like, wow, I'm so glad that this is what we have on the test. So the test would be easier. So don't panic if you're like, oh my gosh, if Steve struggles to do math in his head, are we going to struggle? No. You'll be fine. You'll be fine. Okay, so let's do our a minus 4i cubed. So I'm taking, here's a minus 4i squared multiplied by a minus 4i, minus 32 plus 12 plus 20 gives you 0. And here, 16 minus 6 minus 10, 0. 16 minus 6 minus 10, 0. Minus 24 plus 8 plus 16, 0. 12 minus 4 minus 8, 0. And 12 minus 4 minus 8, 0. Minus 40 plus 14 plus 24, 0. 20 minus 8 minus 12, 0. 20 minus 8 minus 12, 0. And so now we're like, happy. In fact, this is a check. You can check to see if you did your matrix multiplication right, because if all the eigenvalues are 0 on a 3 by 3 matrix, by the time you hit the cubed, everything has to be 0. If all the eigenvalues are 0 on a 2 by 2 matrix, by the time you hit your square, everything needs to be 0. So if you don't hit 0, well, mistakes were made. All right, well, what's the point? Why is this nice? Well, once something is all 0, what it says is everything from where you start being 0 on is going to go away. So that says we can compute e to the a minus 4it, because that's our b here, by just looking at the first 3 pieces. So in particular, what we have is the following. We can say e to the a minus 4i times t. Well, it's the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1, plus the matrix a minus 4i, 8 minus 3 minus 5, 6 minus 2 minus 4, 10 minus 4 minus 6 times t, plus, take the matrix b squared, minus 4, 2, 2, minus 4, 2, 2, minus 4, 2, 2, times a half t squared. And we put it all together. So we're now ready to write down our final answer. Namely, we have, don't forget the e to the 4t, so e to the 4t times, and now we just go entry by entry. So it'll be 1 plus 8t minus 2t squared. The next entry, 0 minus 3t plus t squared. And in the last entry, 0 minus 5 plus t squared. Okay, next row, 0, 6 times t minus 2t squared. So 6 times t minus 2t squared. 1 minus 2 times t plus t squared. So 1 minus 2t plus t squared. 0 minus 4t plus t squared. And occurs to me, I forgot a plus sign here, minus 5t plus t squared, right? Minus 5t plus t squared. Last row, 0, 10t, and minus 2t squared. Then we'll have 0, minus 4t plus t squared. And lastly, we'll have 1, minus 6t, and plus t squared. And there we go. That's our answer. Ta-da! All right, good. Now, if you're looking at this, you might be like, what's our other means? Do we have other means that work? And the answer is, yeah, we actually do have other means that work. We can do it by doing a fundamental matrix, for instance. Namely, we can solve x prime equals ax. And what you'll see is that this is an this is a matrix where we only have one eigenvector, and then you sort of bootstrap to get your, generalized eigenvectors. And so you can find phi, and once you have that, you can find e to the at. But this is actually probably, among all approaches, the fastest. The only thing that makes it slightly challenging is you have some large numbers here when you do the matrix multiplication. Again, on an exam, we'd give you either a lot simpler numbers or a 2x2 matrix. And in both cases, things would be much, much nicer. Okay, all right. Well, let's move on to number 5. So, and we see we're into our Laplace stuff. So we're like, mwahaha, we've got our table. And so we're going to be having that handy in case we need it. When we probably will need it pretty soon. So, what do we have? Well, we're trying to find the inverse of Laplace, 27s plus 18, upstairs, s over s squared plus 9 downstairs. Now, the thing is that when it comes to our table, the only way we can do the inverse of Laplace is if it looks like something on our table. And looking at it, well, we have things like 1 over s. That can be handled. There's 1 over s right there as well. And s squared plus 9, that would be, where is that? Oh, sine, or maybe a cosine. So we say, okay, we have to make it look like these kinds of things. The problem is that there's multiplied together downstairs. So we got to pull it apart. And how do we do that? Partial fractions. So be ready to pull out partial fractions, because that's a very common thing that happens when you're dealing with Laplace transform problems. Okay, so what's the idea? We have 27s plus 18 divided by s times s squared plus 9. So we're going to break this up into two pieces. The something over s and the something over s squared plus 9. And remember, if it's just what we would call a linear factor, just a constant, if it's an irreducible quadratic, you have upstairs is a linear. Really, there's another check here. See how downstairs this is a cubic? That means we should have 3 things to figure out. So whatever the power is downstairs, that's how many unknowns you should have upstairs. And so that's sort of a built-in check. So we need to find A, B, and C. All right, well, so the first step is what we just did, and that's, in some sense, it's the hardest. Once you find that first step, the rest of it's kind of mechanical. And the first step is like understanding. So the first step is get the right form. And so this is, recognize what's your factors here and get the right pieces on the other side. In this case, we were in good shape because there was nothing repeated. So there wasn't like an s squared. If there had been an s squared, we had to say, oh, okay, like a over s, b over s squared. But in our case, we're okay. All right, so this is what we have here. Okay, well, from now, the next step, clear your denominators. So 27s plus 18, all right, is what? Well, imagine that you multiply everything by the denominator. And that would be a times s squared plus 9 plus bs plus c times s. Just think about what doesn't cancel. And now there's a couple of ways you can do it. And you can do some mixing and matching. You have to solve for a, b, and c in some way. And so what are some options? Well, the two main ones that we'll use most often is choose good values and look at coefficients and make the coefficients match up. I always like to start by choosing good values and use as much as we can before I jump to something else. Good values are there any numbers that make things go away? In other words, make zeros. There's a really good candidate here. 0. 0 is a wonderful candidate. So if we choose s equals 0, what happens? Well, over here we get 18. Here we'll get 9a, and then that part goes away. So we say, aha, a needs to equal 2. All right, so now progress has been made. We know what a is. There's not really any other good values that knock out a lot of terms. And so in that case, let's switch gears. We're allowed to switch gears. And in the way we switch gears is we say, well, let's take this right-hand side and we're going to expand it. I'm going to use the fact that we know a equals 2. And so that would equal 2 times s squared plus 18. So that's multiply through, and remember that a equals 2. Plus b times s squared plus c times s. Well, we'll get 2 plus b times s squared plus c times s plus 18. And now we play our matching game. Coefficients have to match. So the 18 has to match with the 18. No surprise there, already does. The 27 has to match here. Like, oh, all right. Well, great. Now we know what that needs to be. And then the 2 plus b has to match, well, we'll just put a 0 here. So that matches there. So now with this, we can read off. We see, aha, b needs to be minus 2, and c needs to be 27. All right. So what do we have? Well, what we have now is the following. We can say, let's just catch up, the inverse Laplace transform of what we started with, 27s plus 18, over s times s squared plus 9 is the inverse Laplace of, and now we use this form here, and we use the constants that we know. 2 over s plus minus 2s plus 27 over s squared plus 9. Okay, so that's the partial fractions. We're going to do a little bit more here. For the s squared plus 9 term, we're going to break that into two parts. So Laplace inverse, and we'll have 2 times 1 over s. Then we'll have minus 2 s over s squared plus 9. So I'm just thinking of the constant, sorry, the part was just the s. And then there's the last part. Now the last part, it's a plus, and downstairs we have s squared plus 9. Now if you think about the form, if you have an s squared plus 9 downstairs and a constant upstairs, that's the sign. And we say, okay, we really want there to be a 3 upstairs. So we're going to make it a 3 upstairs. Well, we have a total of 27. So that means there's 9 left. So I'm breaking the 27 apart. And I want to do it in such a way that I match what I have. And now, if we look, we can do the following. We say, all right, 2, 1 over s goes to 1. So it's 2. Then minus 2, s over s squared plus 9. Well, that's here with a equals 3. So that would be cosine of 3t plus 9. And then we have 3 over s squared plus 9. Well, that's this form here was a equals 3 again. So 3 over s squared plus 9, which corresponds to sine of 3t. And we're done, right? Because we actually went and found the inverse Laplace transform of what we needed to do. And so there we go. That's not so bad. I mean, really, it's mostly just a matter of saying, do you understand what you need to do? Key is pull it apart so that you can find the pieces on your table. And then, of course, know how to use your table. And we won't use the whole table, but you want to figure out, okay, what's the right form? You know, these are molds. You know, which mold does this fit into? And once you can figure that out, life is pretty good. All right, good. Well, that's number 5. Well, not much left to do. Well, a little left to do. Number 6. Given x double prime minus 2x prime plus x is delta of t minus 1 plus delta of t minus 2 with x of 0 equals 0 and x prime of 0 equals 1, then find x of 3. Okay, well, what's happening here? We have something starting off initially, and then at time 1, we hit it with the delta function, which means there's a big boom. There, we sort of, there's an impulse, bow, at time 1. And then we're saying, okay, and then at time 2, another one, boom, a second hit. And now we're saying, okay, what happens at time 3? And so it's a system which has undergone a little bit of behavior in the first few beats, in some sense. So what do? Well, we start by going to our table here. And we're going to use our inverse Laplace and work through it. And we notice we have an x double prime, so that's good. So we're going to take the Laplace transform of both sides, x double prime minus 2x prime plus x. That's going to be the Laplace transform of delta t minus 1 plus delta t minus 2. Well, all right, this is the Laplace transform, x double prime minus 2, Laplace transform x prime plus the Laplace transform of x equals Laplace transform of delta t minus 1 plus the Laplace transform of delta t minus 2. Not much has happened here. What we've done is just said, oh, let's use linear things. And now we come into our table and we start reading off. So for x double prime, it would be s squared x of s minus s times x is 0, but x is 0 is 0, and minus x prime is 0, which is 1. So the first term is going to be s squared x of s minus 1. Okay, so that's x double prime, using our initial conditions as well. Now x prime, well, that's going to become minus 2, and it would be s times x of s minus x of 0, but x of 0 is 0, so it will be s x of s and plus x of s. Now that's going to be equal to, on this side, delta of t minus 1, well, delta of t minus a, e to the minus as. So it would be e to the minus s, and here, e minus 2s. And all right, so now we've done our transform. And we just need to clean it up a little bit. So let's do that. Not much to do. The minus 1 will come across, and then we gather. So it's s squared minus 2s and plus 1 times x of s is equal to 1 plus e to the minus s plus e to the minus 2s. Right, the 1 went across, and then we just gathered the terms with x of s. And, well, this is nice. This is really s minus 1 squared. Okay, great. And so now we're ready. We can say, aha, x of s is 1 over s minus 1 squared plus, well, I'll just keep writing as 1 over s minus 1 squared e to the minus s plus 1 over s minus 1 squared e to the minus 2s. And now we need to figure a couple things out. What is 1 over s minus 1 squared? If we think about it as what's the inverse Laplace transform of that? So we start looking at our chart and say, what does it match with? Well, it's going to actually have to match with something here. And, oh, there we go. It was over here. 1 over s minus 1 squared. Perfect, right on our chart. What does it match to? It maps to t e to the at. Now, in our case, a is 1. So this part here should really correspond with t e to the a, sorry, well, 1t. A is 1. All right, great. Now, you'll notice it's the same function here, but what does the e to the minus s do? Well, now we say if you have some function multiplied by e to the minus as, it's a shift. So here, this says shift by 1. And here you have the same function, t e to the t, and the e to the minus 2s says, oh, you need to shift by 2. So if we put this all together, what do we have? Well, we have, taking the inverse Laplace transform, we get x of t would be t e to the t. All right, that's good. And then what? We're going to have t e to t shifted by 1. So that's going to be, when we shift by 1, replace all the t's by t minus 1, e t minus 1. And then there's one other piece. We have to have that on-off switch, u of t minus 1. And here, similar thing, t minus 2, e to the t minus 2, because we're shifting by 2, but turn the on-off switch u of t minus 2. All right, so there we go. This becomes that. And you'll see it's the same function, t e to the t, consistently all the way across. The only thing that really changes is you have to hit it with these on-off switches. Now, what are we after? Well, we want to know x of 3. So we can write it down. So we plug in 3. So we get 3 e to the 3. That's not too surprising. Now plug in 3 minus 1, we get 2, so that's on. So we need to plug in this part. Well, that would be 2 e to the 2, right? 3 minus 1, e to the 3 minus 1. And 3 minus 2, that's 1, so we're on. So right, anything above 0 is on with the u function. And now plug in 3. 3 minus 2 is 1, and e to the 1, so plus e. And that's our answer. That's our final answer, because that was our final problem. And we're done. Woohoo! Yeah! Not too bad, not too bad. And of course, the more we practice, there are more practices, better we get. So keep practicing, and things will become more natural, and you'll do great. See you later.